Hello, everybody. My name is Andrii Mironchenko. Welcome to my talk on construction of ISS Lyapunov functions for infinite networks. This is a joint work with Christoph Kavan and Majid Zamani. We live in the world of networks. We're surrounded by manufacturing networks, electrical grids, transportation and social networks, and emerging technologies like 5G, Internet of Things, or cloud computing make the size of such networks larger and larger. The safety and reliability of such networks need to be analytically verified, but existing tools do not always scale to complexity of such systems. At the same time, infinite networks capture the essence of large but finite networks of unknown size, and hence it is of virtue to study the stability of such infinite over-approximations. Today, our question will be, under which conditions is an infinite interconnection of nonlinear stable systems itself stable? We provide several tools how we can approach this problem. In this talk, I will explain the general nonlinear small gain theorem for infinite networks. In this result, we assume that the subsystems are nonlinear and also the interaction of these subsystems is of nonlinear nature. We also do not assume any kind of spatial invariance assumptions. And for this class of networks, we show that if the interaction between subsystems satisfies the small gain condition, then the whole network will be stable. Furthermore, we can construct a Lyapunov function for the whole network if we know Lyapunov functions for subsystems. This result fully generalizes the small gain results for finite networks. If the interaction between subsystems is of linear type, then one can refine these results, and I will explain this in my second talk in this session. Although I will speak about systems with ODE components, but we can treat also general networks whose components can be ODEs, PDEs, delay systems, etc. So, we consider in this talk the interconnections of infinitely many systems of such type. So each subsystem is an ordinary differential equation. Xi is its state. Xi bar is the vector consisting of the states of neighboring subsystems. So this is internal input to sigma I, and Ui is external input to sigma I. We assume that Fi is continuous and such that this system is well posed. To define the whole network, we collect Xi, Ui, and Fi into vectors x, u, f, and now the equations of motion for the whole network have this form. To fully describe the system, we define the state space as an L-infinity sum of the state spaces of subsystems. We define the space of input values also as L-infinity space, and the input functions will be piecewise right continuous and such that L-infinity norm is finite. We consider Kara-Teodori solutions for this infinite ODE system, and we assume that it is well posed. To define the stability properties, we need two classes of comparison functions. We say that a function is of class k infinity if it is continuous, 0 and 0 and increasing. KL functions are continuous functions of two arguments, which are like k infinity in the first argument and decay to 0 in the second one. Now we define the main stability notion for this talk. We say that a system is ISS, or input to state stable, if the norm of the trajectory can be upper bounded as a sum of two functions. Beta function of class KL, describing the transient behavior, and k infinity function gamma, describing the influence of external inputs. So if we start somewhere here, then our trajectory is upper bounded by this sum. And since this guy goes to 0 when t goes to infinity, then our trajectory approaches the ball with the radius gamma of norm of u around the origin. In this way, input to state stability unifies the the asymptotic stability in the sense of Lyapunov and input to output stability. The main tool how we can analyze ISS are Lyapunov functions. A continuance function is called a Lyapunov function if it satisfies such sandwich estimates for all x from the state space, and if such an implication holds. It tells us that if x is large enough with respect to u, then the derivative of v along the trajectory is negative here. So this means that the Lyapunov function decays along the trajectory if state is large enough with respect to input. It is not hard to show that existence of such a function implies ISS, and if f, the right-hand side, is regular enough, then also the converse holds. So Lyapunov functions are a great tool to study ISS, but it is not easy to construct them. And if we have an infinite network, then it is even harder. So therefore, what we are going to do? We assume that all components are input to state stable, and we know Lyapunov functions for all components. So we have infinitely many functions vi, which satisfy sandwich estimates. I assume that they are uniform in I, these functions, psi1, psi2. And again, we assume that Lyapunov function vi satisfies this inequality. So this means that if xi is large enough with respect to the total input to ith subsystem, then the corresponding Lyapunov function decays along the trajectory. So here, this term is very important. Basically, gamma ij tell what is the influence of the system j to the system I. Since this term is important, we define the so-called gain operator in this way. So basically, we take this expression, and instead of this vector of values of Lyapunov functions, we just take arbitrary some vectors in L infinity plus. So in gamma maps L infinity plus to L infinity plus. So we assume that this family is pointwise equicontinuous, so this operator is well defined at continuance. And now it turns out that the question whether the whole network will be stable or not will depend on the properties of this operator again. We will need one more definition. We say that a map sigma mapping R plus to L infinity is called a path of strict decay for gain operator gamma if all components of this sigma are K infinity functions, they are bounded from below and above, and most importantly, gamma decays on the image of this sigma, right? So this guy is less than identity, and so gamma decays on sigma of R for all R. Well, we have a condition how we can prove that there is such a path of strict decay. We take a gain operator, we scale this operator by some here K infinity function. If the corresponding this scaled gain operator generates a uniformly globally asymptotically stable discrete-time system, then there is a path of strict decay for gamma. Okay. Furthermore, we can show actually even more. We can construct this path of strict decay. So one more time, we take gain operator, we scale it in this way, define this scaled operator gamma theta. We assume that this system is uniformly globally asymptotically stable. Under such conditions, such an operator Q is well defined. Q maps initial condition to the supremum of the corresponding trajectory of this system. Now we can define sigma in this way, and one can show that the sigma is in fact path of strict decay. So what is important that we have explicit construction for a path of strict decay. Okay, so I omit all the details here. Now we can formulate our nonlinear small gain theorem for infinite networks. Assume that we have a well-posed infinite network with input to state stable components and assume that we know the ISS Lyapunov functions for all subsystems. And these functions satisfy these assumptions, which we have already formulated above. From the gains gamma ij, we construct a gain operator gamma, and if this gain operator has a path of strict decay, then we can construct an ISS Lyapunov function for the whole network using this formula, and thus the whole network is input to state stable. Let me conclude our developments. If we have an infinite network with nonlinear components, with nonlinear type of interactions, and without any kind of spatial invariance assumptions, then we can use our small gain theorem to analyze stability of the network. Then we need to construct the gain operator, and if it has path of strict decay, then the network is input to state stable. This result covers available nonlinear small gain theorems for infinite networks as special cases, and it gives also a natural extension of the known small gain results for finite networks. Furthermore, if the scaled gain operator induces a U-gas discrete-time system, then we can construct explicitly the path of strict decay for this gain operator, and then we can construct the Lyapunov function fully explicitly for our infinite network. We have also some further tools how we can analyze stability of the network. If we do not have Lyapunov functions for subsystems, but we can verify input to state stability of all components, then we can use nonlinear small gain theorem in trajectory formulation, which we have shown in a very general setting of multi-physics systems with ODE, PD, delay components, etc. If our gains are linear, then we have somewhat more handy small gain conditions, about which I will talk in my next talk in this session. Also, we have applied these results to distributed control and observation of infinite networks. I conclude my talk with a list of references. So this first paper is where the main result of this talk is proved, and these are some related results on small gain methods. Thanks a lot for your attention.